from Meta. So Dr. Tian is a research scientist and the senior manager in Meta AI research where working on reinforcement learning, optimization, and understanding of neural network. He has been the project leader for story generation 2023 and Open Go project 2018. He's the first author recipient of 2021 XML Outstanding Paper Award, honorable mentions, and 2013 SCCV Mar Prize honorable mention, and also received 2022 CGU Distinguished Paper Award. Prior to that, he worked in Google self-driving car team in 2013 to 2014, and received a PhD in robotics Institute CMU in 2013. He has been appointed as the area chair for URIPS, SML, Triple AI, and AI stats. So today he will talk about research, recent latest result about transformer, how to understand transformer, and the application to large language model. Now, it's yours.
Okay. Thanks, Bing, for the introduction. Should we start?
Yeah.
Okay. Yeah, so let's start. Konnichiwa. Thanks everyone for being here and to listen to my talk. And I was particularly thankful for Qibing for take care of me, right? So I was a little bit hurting in the left legs and was not able to walk too much. But thanks everyone for helping with that out and recovering. Okay, so today I'm going to talk about demystifying attention in multi-layer transformers and also its application in better inference in larger models. Okay, so let's start. So we all know that larger model is being used everywhere. Yeah, we know that we can use larger model for content creation, for AI agents, for copilots, right? Lots of things. So if you check like a good news, different news in Twitter or like in like Hacker News or like in Y Combinator, you also see many different kind of scenarios. Like every time you see a big boost in large models, it actually will influence many different scenarios, and the people are really like to see this happen all the time. So if you think about how should we contribute the community for larger models, I think one thing that we probably want to study is transformers. Right, so we all know that modern larger models, they all use transformers as their backbone in order to predict the next token or do different kind of tasks. Right, so in transformers, one of the key components is attention. So here, this is a linear transformer presented in 2017 by this famous paper called Attention for All You Need. So in that paper, they use the encoder-decoder framework. Right, so they first encode the sentence, and then decode a sentence in a different language so that they can fill for the machine translation tasks. Right, so in this kind of architectures, what happens is that you have this attention mechanism. So you have a query and you have a key, and then for every new query, new token that will be inputted into the transformer, and will basically attend to all the previous tokens that has been seen. And then you use that as information to basically weight the current tokens embeddings. Right, so for encoder side, you basically attend to both sides, and for decoder only architecture, you only attend to the previous tokens that you have seen before. Right, so this attention mechanism play like the magic here. It basically like try to combine different features into the tokens and combine like contextual features into the current token so that the current token actually convey methodological information in the token embeddings. And if you stack them in multiple layers, and then eventually it will learn on the high level concept, and use the high level concept, you can predict the next token or do a lot of different tasks. So this is actually, and one of the interesting components for the attention is the sparsity. So the sparsity actually comes everywhere. So here's like one of the top oral paper we had in our previous in this year's ICML, is that we try to basically leverage the sparsity. We basically first observe the sparsity, and second we try to leverage the sparsity to basically improve the throughput of the feed forward in larger models. Right, so you can basically both. Right, so in this talk, we're going to cover, first of all, how can we leverage like attention, leverage the sparsity in attention, and understand the sparsity in attention. And second is how we leverage that in different applications. Okay, so here's the first part, understanding attention mechanism. So for that part, we'll talk about like 2 papers that we've been working on to understand attention mechanisms in transformers. The second part, we talk about the applications using attention sparsity to make the inference faster or make the inference more efficient, in particular for a long form and long context generation. So let's start from the first part, right? So we always start with simple things, right? So for theoretical analysis, it's very hard to understand the entire transformer architecture in its current form. It has a lot of components, very complicated, right? So what you can do is to start with 1-layer settings. So we have a bunch of like contextual tokens, and you have a query token. And then there's a self-attention layer. And after self-attention layer, you basically combine these tokens bind together, and then we go to normalization. And finally, and we'll go to decoder and then predict the next token. That's very simple settings. Okay. And this paper will be accepted in Europe this year. So first thing is that even this setting is complicated, so we try to reparameterize the entire problem into a very simple 2 parameters. One is called decoder. This is Y. So basically, that's all the parameters after the self-attention layer. And the second is Z, which is basically the parameters in the self-attention matrix. Right? And if we do that, then it turns out that the dynamics becomes much easier to analyze. And we have this kind of formulation for dynamics. It looks very crazy, right? So all this looks pretty complicated, but that's fine. I'm going to tell you the high-level messages in today's talk, right? And you don't need to go through all the details. And if you are interested, feel free to check details in the paper. Right, so we also made major assumptions. First of all, we don't put the positional encodings. We assume that all the contextual tokens, they are equal. They can swap with each other. And also, we assume that the sequential sequence length T goes to infinity. Right? And also, we assume that learning rates of decoder is faster than the learning rates of the self-attention layers. And this will be, we will get rid of this one in the second paper. And we also have other technical assumptions. We also assume some distribution structures, right? So we assume that there's a bunch of next token categories. Each category corresponds to different distributions of the contextual tokens. Right? So we can treat this next token prediction as a classification problem. For each class, it will output a different token as a next token, and given the next token distribution of all the contextual tokens, they are also very different. Right? So in this distribution, we're going to see 2 different kind of tokens. One is called distinct tokens. These tokens only appear in one sequence class, but not in other sequence classes. Okay, these are distinct tokens. And these tokens, called common tokens, they appears in multiple sequence classes. Right, so they have 2, and in the future, you're going to see there's 2 different fate for these 2 different tokens. Okay, so here's an overview of the training dynamics from this paper. So first of all, we define this quantity called a C titer. A quantity actually has 2 different components. The one is basically modeling the co-occurrence probability between the query token M and the contextual token L. And the second is that component. Right? So this Z is actually an attention of the attention logics between the token M and token L. Okay. So at the beginning, if you basically like draw this C titer, you will see this kind of very simple distributions, right? You have a very frequent tokens that is higher, and then low frequency tokens that are lower. And all the attention score, they are zeros. Then after the training, we can show that, first of all, for common tokens, their attention score will go down. They will be suppressed because these common tokens is appearing in both sequence class 1 and sequence class 2. So they are not that useful in predicting which sequence class it is for the task So this common token basically will be suppressed in terms of the attention scores. And second, on the other hand, for distinct tokens, you're going to see like the attention score will go up. Once they go up, and you're going to see that, this actually give you a different picture, right? So this gave you the feeling that the self-attention is like a learnable TF-IDF. So TF-IDF is actually a term that people use for natural language processing before the deep learning era. So in TF-IDF approach, it's very simple. It will try to get rid of the tokens that has a lot of frequencies in all the documents, like common tokens, or like articles. But at the same time, you also want to emphasize on tokens that appears specifically for the sequence class. And at the same time, it's pretty frequent within that class. So attention is doing exactly like that. And moreover, and attention actually give you a kind of more fine-grained control for a kind of TF-IDF kind of style of filtering, right? Because we can also prove that if a token is high frequent in one of the class is very distinct, then the attention score will go fast. Then other tokens that are also distinct, but rarely happens with the query tokens. And we actually prove the growth rate for all these attention scores, right? So it actually grows faster with larger core curve probability, right? You can actually prove all this, and you can also bound this kind of growth rate, right? So this chi is the growth rate between these two tokens, air and air prime, and these are basically all distinct tokens, right? So you can actually get this bound there, right? So and the consequence of this dynamics is that they will going to create this contextual sparsity, right? So this sparsity depends on what kind of query token it is, right? So if you have a different query, then you're going to see very different patterns in terms of sparsities, right? So, and then we're going to see that this contextual sparsity will be very useful and important in the next application component. Okay, so come back to the series side, and we can actually like a bound. Okay, what is this BN that drive this growth of attention patterns? And you're going to see two stages, right? So at the beginning, there's a called attention scanning. In that case, this B grows in a logarithmic manner, so that this exponential with respect to this BN is growing in a linear rate. So the attention becomes faster. But over time, right? So when everything passes threshold, then the attention will have this attention snapping phenomenon in which this BN basically grows in a log T rate, which means that exponential of this BNT will grow in a more exponential rate or in a logarithm rate. So basically, this case give you this kind of feeling that at the beginning it grows and then it stops somewhere. It takes forever to grow faster, right? So what you see is that the attention pattern will become sparser and sparser, and at the same time it frees and never become one hot, right? So that's basically the structure of the attention, and we characterize the structure when the self-attention layer is there, and then so when the decoder is linear, right? So that's basically the main content of that paper, and we also tested in the real experiments and show that yes, it seems to be the case for real world models. Still very toy, but real world you see the attention pattern like that. Okay, so I have finished introducing this paper. This is called the scan and snap. Right. So, but still we see a few very annoying assumptions, right? So because there's no residual connections, no embedding vectors, and also there's this kind of constraint that the decoder needs to look faster than the self-attention. Right, so how to get rid of them? So recently we also have a follow-up paper called the JORA. And this paper is able to get rid of many of the assumptions, and at the same time it was able to give quantitative analysis for multi-layer attentions. Right, so for this paper, what we do is that we actually find a joint dynamics that can combine the lower layer of MLP and also a self-attention together. Right, so now the self-attention comes with residual connections. Good. Because everyone knows this is important. And we also have MLP lower layers, and the JAMA actually find a way to combine them together into a modified MLP lower layers. And by analyzing this one, we are able to analyze the multi-layer behaviors of the multi-layer transformer network. Okay, so here's a very simple settings of JAMA, right? So you have an X, which is input, and you have a self-attention layers, and then you also have residual connections. And then once the residual goes to residual connections, and this F goes to MLP layers, and then there's also nonlinearities, right? So this is not there in the previous scanner snap paper, in which we assume linear connections. Now we have nonlinearities there. And this softmax and this attention, you can have multiple different attentions, right? You can have softmax, you have XP extension, also linear attentions. And you can see JAMA can works in these scenarios. So this is the first theorem that you can actually prove with JAMA. First of all, we can actually show the dynamics of the lower layer of MLP and also self-attention. If you combine them together, there's actually an invariance of dynamics, which means that if you do integration, you will see that the self-attention score is related to some transformation of the weights over time. And for different attention, you're going to see different expressions, right? So for linear, both are square, and for XP, then you have ZM equals to like a square of the summation of all the top layer. Self-attention similar, but still in self-attention there need to be some assumptions, because self-attention has some terms that need to be cancelled out. Okay, so that's good. Then in that case, we end up with a good analysis in the presence of residual connections. And you don't need to assume that the top layer is trending faster than the lower layer in the same attention block. And there's no assumptions on there are some distributions as well. Okay, so once we have that, then first of all, okay, we need to verify, okay, this is true or not, especially for self-attention being a softmax. Right? Because in softmax, you see a bunch of like assumptions. Right? So this assumption doesn't seem to be that natural. And I tried this for multiple like synthetic examples. Right? So this is a synthetic example. First of all, you set up the distribution of X, the input patterns, and check like whether the predicted self-attention score is the same as the real self-attention score if you actually run dynamics in the real settings. You see like the correlation actually very high, it's almost 100%, right? So which means that it's actually good. And if you basically take two of the component out in this expression, and then compare the correlation, and you see the correlation is lower, which means that you need to combine these two together in order to get 100% correlation, right? So which means that this expression really captures something important. Okay, so once you have this kind of formula, right? So you have the JAMA formula, you basically combine self-attention with the lower layer of MLP, and you can do a lot of things. Right? So now we have a new tools to analyze all the information. So first of all, I want to see okay, whether this will recover our previous results. Right? So in our scanner snap paper, what we say that is that the self-attention will become sparser and sparser over time. Right? So maybe in JAMA things are different, and then it's conflicting to each other, and it's bad. Right. So first of all, I want to show that with JAMA in this framework, this one is still giving the same results. Right. So once you have the previous expression, what you do is that very simple. We know this is self-attention property. Then when we write down the MLP formulation, we know that self-attention is basically another term that can be replaced by the MLP's dynamics, right? So this actually leads you to this following dynamics, right? So you basically check whether these following dynamics give you the sparsity that you want. Right? Okay, so for linear case, it turned out that it is actually the same as the previous previous analysis. Right? So in linear case, it turned out that this delta M is actually constant if things are linear. And this delta M is actually a product of the two terms, right? So one is the co-occurrence, and the other is the discriminancy. So this basically corresponds to the common tokens versus unique tokens in our previous analysis, right? So it's actually, and also extend the previous analysis to more continuous spectrum. That's good. In this case, we basically can prove that there's some expression between the two tokens. And this expression basically tells you only one component of V will go to infinity, and other of the component, they will stay finite. Right? So basically, eventually you're going to see winning take all over time. Right? So actually, this is much cleaner than our previous analysis. And with only a few lines of proofs, things are getting very clear, rather than a lot of complicated kind of analysis. So this is a good announcement compared to the scalar step. Okay, so this is also like some visualizations, right? So if I tell you only one component will grow, then the rest component will stay finite. Okay, here's the proof visually, right? So one component goes to infinite, and then the remaining component, they just stay finite. Right, so this is really what's happening if you run the attention mechanism and attention dynamics in the synthetic data, and you're going to see a very simple and also consistent analysis and results compared to the theoretical understanding and also analysis. Okay, cool. Okay, then more interestingly, like what will happen for non-inactivations, right? So this is something we really want to see, because this is the motivation for us to bring about this grammar framework. Now we have a cleaner formulation, and we can use that formulation to analyze something that we cannot reach in our previous analysis. In that case, we can actually show that this dynamics becomes something different, right? So you have this, instead of having some delta m that is constant, then you actually have a stationary point, right? So that's somewhere, and that stationary point is actually stable in some circumstances. Right, so and once you have that, then you add this self-attention. The self-attention is still exp v squared over 2. So then what happens? It turned out that the dynamics become different. Right? So it becomes that the attention first becomes sparser, then it becomes denser. Right? So it's actually interesting. So because if you check this dynamics, if you get rid of this exp, then you know that it will converge to mu. Mu is some kind of like a pattern you want to learn in your data, right? So this pattern will have multiple components, right? So some component corresponds to token that is high co-occurred with your query. But there's some other component that does co-occur with your query a lot, right? So if you solve this entire curve in the co-occurrence, so this mu is solid in kind of a smaller to larger manner. And you're going to see like the salient component get converged very fast, right? So you don't see any kind of redness here. Redness means that very high iteration numbers, right? So this actually converge very fast, but this small component actually converge very slowly, right? So you see like this redness here. Redness correspond to like higher iterations, right? So you're going to see at the beginning, the reason why attention goes sparser is because you only basically learn the component that is co-occurring with the query a lot. And you see that, and the things become sparse. But why it got become dense again is because, I mean, all the small component, non-salient component, they will catch up later. Right? So they will, once you train it for a long time, it will start to catch up slowly. And then that's why attention becomes denser over time. So that's basically the reason why you see this kind of patterns. And people will say, oh, okay, this is the synthetic examples. How about the real examples? Okay, here are the real examples. So you train with your multiple layer attention and multiple transformers on Wikitext 2, Wikitext 103. And then you will see very clear this kind of curve. Right, so things drops a little bit and then go up again. Okay, it happens to 1 layer, 2 layers, 5 layers, and also 10 layers as well. The only difference here is that on 10 layers, the lower layer, which is shown in purple and blue, they are kind of bouncing back behavior is getting suppressed a little bit. Right, they're getting suppressed a little bit, but still the top layer having this bounce back kind of behaviors. And we also check all the pre-trained models, including like PySeer and also PT. these pre-trained models, they are basically providing you with all the intermediate checkpoints, right? So because they have intermediate checkpoints, you are able to check these checkpoints and see whether you see the same behavior, right? So you see the same. Oh, thanks. So you see, like the same behavior actually persists, especially if you check the stable rank of the lower layers. Because in our previous analysis, JAMA, the lower layer of MLP is linked with the attention structures, right? So, and basically when the attention becomes sparse, the rank of the lower layer also becomes lower. Right? So you want to see like this rank also has this bouncing back behaviors in different structures, which is good. So it shows the consistency between theory and practice. And actually, we also prove there's actually a convergence rate difference between two components. One is salient and the other non-salient. Right. So we actually prove that the convergence rate of those two components is actually proportional to the exponential of the actual magnitude, and taking the power of exponential. Yeah. So you have these kind of instructions. Okay. So okay, we have shown this is the case. But then the question is that why you have this multi-diagonal properties, right? So
Yeah, ask the question.
Yeah.
Maybe you can, I will ask the question and you can take time to drink the water.
Okay.
So the sparse denominator is very interesting to us. So my understanding is in the linear case, the attention will become sparse and sparse. But in nonlinear case, it first becomes sparse and then dense.
Yeah.
So what that means? Can you give us more intuitive understanding, like what's this phenomenon? The inside.
Okay. Yeah, sure. So I think this figure actually show you some of the why this is the case, right? So this figure basically says, first of all, the target mu is a stationary point. It basically corresponds to some patterns in the data, right? There are some patterns that is very salient. For mu is a high dimensional vector. That vector, every entry of the vector corresponds to, for example, the co-occurrence of that token with respect to the query. Right. So, and there is some component of mu that has a high co-occurrence with the query, and also highly distinctive with respect to the query as well. So they are basically the leading component of the pattern. But there are some other kind of patterns that are also co-occur a little bit with the query, and also has some distinguishing power with the query as well. So these two components are actually pretty weak. Basically, they are very close to zero, but still non-zero. They have two different components like that. I'm not sure whether that's clear or not. Yeah, if you check what's the component, you actually you can think this way, right? So for every token L, you have first of all the probability of L given the query. This is basically co-occurrence, right? And second is basically this one. This basically tell you how distinctive given the token L and M for the output. So G is basically the backproper gradient, right? So this term can be zero, which means that this token happens in different classes, right? So in that case, even this token co-occur with the query a lot. This token does not really matter that much, right? So and also you also want this token that co-occur a lot, which means this is high. At the same time, it actually is very distinctive, right? So it has a very high value in terms of this G, and very high, very high positive, a very high negative, a very low negative, right? So this basically can be measured as in some sense discriminative power times the co-occurrence for each kind of tokens that you want to use. Yeah. So if you think it like as a linear attention, you can think this is a feature of the linear features. The higher this linear feature is, and the more valuable this token is. Right? Yeah. And this mu is actually proportional to this data. Right? So we switched it a little bit, and so this may make people a little bit confused. Yeah. Okay. So and we also show that yeah, if you have like a higher if you go back to these slides, so for the higher component of mu, then the convergence is fast, right? So it converges, for example, in maybe 1,000 iterations, right? So this is shown in purple. In that case, you're going to see a very high convergence, fast convergence rate. So after 1,000 iterations, then what happens is that you only see a few components goes up. The remaining component actually goes still stay very low. That's the reason why it becomes very sparse, right? So around like 1,000, you see attention entropy is sparse. But overall, because this part is being converged, okay, it will stay there. But this kind of weak component, it will basically slowly catch up, right? So it will slowly catch up. So once it catch up, you see the attention entropy goes up again. Right? So that's basically the mechanism why you see the attention becomes sparser and denser. Okay. Any other questions? Okay. If no other question, then I'll go to next slide. Again, the question is like, okay, this kind of property is shown right now, but why it is useful? Right. So one question is that in one layer, I mean, we don't need that property because it will only slow down the trading. Right. So because if you think about everything as a linear classifier, you see very strong features, and also you see very weak features. The best choice for linear classifier is to have a weight that is proportional to the usefulness of the features. Right? So you don't want to get rid of all the small components, but you want the ways to also capture all the properties of the input features. So I think in the paper, what we discussed is that maybe this property is not useful in one layer, but actually it's useful in multiple transformers to learn the hierarchical representation of the data. Right? So the reason why this is the case is because if you think data being generated as hierarchical models, so you start from this class label y0, and then this class label will basically hierarchically generate all the latent variables that represents some semantics of that class labels, right? So the simplest thing we can think about is like envision. This may be a class. Okay, you have this is a human, right? So y0 equals to 0, it means that's a human. Then in this human, then we know, okay, given this is a human, we're going to generate all the limbs, the head, face, and also and the smiling, and also expressions, etc. You have the hierarchical latent variables you want to fill in order to generate an actual image of a human. Right? So all these latent variables, they are hidden. You don't see them, and there's no label, and you need to figure that out by yourself in the training. Right? So you basically assume there's a hierarchical structure of the data. And then you can actually show the hierarchical structure as leads you to a very strong co-occurrence between the tokens that has a very close in terms of the hierarchy. But the co-occurrence between tokens, for example, M and L prime, this co-occurrence will be very low if their common latent ancestor is very high. Right. So you can actually prove this is the case. I mean, it is there's actually an actual expression for this. Right. So if H is small and L is huge, right? So you have a huge hierarchy, and your kind of common latent ancestor is very, very low in terms of hierarchy, then this one is almost one, which means that the co-occurrence between the two tokens M and L, they will be very high. And according to our previous analysis, the attention will try to group these two together very, very quickly. So that's good. Yeah, and this is also good for other learning of hierarchies as well. Right? So for example, if you want to learn distribution that has this very deep latent distribution, then what attention will do is that it will basically combine these two in the lower level of hierarchies. Then you combine these two together, and then this will form some kind of representation of the lower level hierarchies. And then once you have this intermediate representation, they will also co-occur a lot because they have a very low CRA, common ancestor. So this is basically be grouped together by the self-attention mechanism. And then gradually it will build this entire hierarchy together from bottom to up. Right? And the reason why the self-attention want to defer the association between these two tokens that does not co-occurrent is because they might belong to two different lower hierarchies. Right? So you don't want to really connect M and L prime immediately, because if you connect these two together, then what will happen is that you don't learn these hierarchical structures, but you learn some kind of spurious correlations between this M and L prime. And this is not good for the learning a true representation of the data. And the attention is able to give you this kind of advantage of learning the correct representation by slowing down the association of tokens that are not directly correlated. So that's the reason why there's a kind of like a deferring or delaying structure in self-attention. You want to learn the co-occurrence of two tokens first. For the two tokens that has a high co-occurrence first, then you learn tokens that has a lower co-occurrence with the query second. Right. So this is the reason why this is the case. And the reason why we want to learn the two tokens that has low co-occurrence eventually is because we want to have an algorithm that is invariant to all distributions, right? So when you have a data, you don't really know what is a shallow data distribution or deep latent distributions. If you have shallow models, then eventually you want to learn the association between M and L prime. Right? So even if they have low co-occurrence, in that case, you basically train the model for a long time until the attention can eventually pick up this M and L prime, and you still learn the data. Right? But at the same time, you also want the same mechanism to work on the deep hierarchy. Right? So in that case, like it still works because these two will be learning faster, and this will be learned faster before you associate M and L prime. So in that case, like a self-attention mechanism can be applicable in both scenarios without knowing which side is which in the data distribution. Okay, so basically this summarizes the DROMA framework. Oh, I already spent a lot of time on that. So we also have a lot of future work, for example, in how to deal with the embedding vectors. We assume the embedding vectors are orthogonal to each other. So we want to deal with the almost orthogonal settings, right? So we also want to basically formally formulate the mix of the multi-layer transformers. In the previous analysis, the quantitative analysis telling you what happens given the mechanism that we analyze in the one-layer settings. Right? So, and we try to apply this to multi-layers and see whether it actually can explain a lot of things. But this will be a follow-up work. And there's some actually other kind of interesting structures that we discovered. So what is called the pattern superposition, right? So one neuron in MLP can be activated by multiple irrelevant combinations of tokens. For example, one neuron is be activated by two different phrases, completely different, but they are all represented in the same neurons, right? So this is very interesting, right? But this is actually can be shown in the theory. You can see like the same embedding can actually encode two different representation of two different phrases. Together, they combine into the same weight vector in the low layer of MLPs. So this is also interesting and can be seen in the analysis. So I didn't really have time to cover that, but if you are interested, you can feel free to check our appendix. It has a lot of interesting component there. Okay, so this concludes the first part, which is basic understanding of the attentions. There's a lot of theories, understandings, and equations. But part two is more about applications. How we're going to leverage the sparsity of attention in order to make the ARM inference much faster. So this one is majorly the correlation is a collaboration with other people about how can we leverage the kind of sparsity in different scenarios. First is called the deja vu paper. And that paper basically is oral in this year's SMR. The paper basically tried to make sure that the inference of the ARM is faster by leveraging the contextual sparsity. So what we do is that you know that you send an input into the multi-layer transformers, and then for every time you send to the input, you really need to compute all the attention heads, compute MLP and hidden nodes, and compute attention heads again until you go through all the layers. It's actually very slow. The reason why it's slow is because most time it's a memory bound. right? So you first have to load all these WQ, WK, WB matrices, and then you compute this attention for different heads, right? So combine them together. You know that while the GPU memory is often like, for example, in A100, it's 80G, the cache is much smaller. The cache of the A100 is usually like 40 M. Right? So if you can put everything into cache and compute, it's actually much, much faster. It takes like only a few CPU cycles, GPU cycles. But you want to wait until you load from the memory to cache. It takes a few thousand, a few hundred memory cycles. It takes longer. So you see like many papers from facial attention, these papers, they would rather recompute everything you backpropagation rather than loading everything from the memory. It's actually very interesting kind of trade-offs in order to make the throughput faster. So here we are doing the same thing, right? We basically say, well, we only want to load the desired set of parameters, right? So for attention, if we can predict, okay, for example, what has actually being used doing this feed forward, and we only load the corresponding rows and columns of these W matrices. And similarly, in the MLP layers, we only load rows and columns of the lower layer, upper layer of MLPs, so that we know only, for example, this neuron 2 and neuron 6 need to be computed. And we can basically disregard all other neurons because we expect the output to be 0, in the, for example, in the value sentence. In that case, we can save a lot of memory loading, and this will basically be a lot more efficient. It turned out that because things are sparse, we are able to do this either by designing a similarity-based prediction. Basically, we start with like for example, a few evaluation set, right? So maybe a few thousand tokens, and then we send this into the attention, send this into the transformers, and we basically record what are the attention heads that be activated, what are the MLP nodes be activated. Okay, so we record them, and this basically becomes your training data. So given the data input, and then given like what are the attention heads that be activated, we basically can train a classifier, or we can do nearest neighbor search. And we use classifier to predict beforehand what the MLP neurons will be activated. And then we basically execute this classification. Then we load only the memories that it will give you non-zero component or non-trivial component. Right? So this will make things much faster. So that's basically the idea of deja vu. So the goal of deja vu is basically to show, first of all, it will give you much faster generation, right? The latency become much slower, so much smaller, right? So compared to existing, for example, Hugging Face implementation or fast transform implementation. And at the same time, the final outcome remain the same. Right? So if you have deja vu, you basically have the same performance for all this kind of metric in larger models. And this further show, we also show that deja vu can be combined with existing quantization and compression techniques. Right? So for here, for example, the W4A16 means that you use 4-bit quantization for weights and 16-bit quantization for activations. So, and this will further improve the speed in terms of latency. And at the same time, it's orthogonal to the existing deja vu approach. Right? So you still see the same or even slightly better performance in terms of different benchmarks. Okay, so that's basically the one of the papers that we have. And we also recently working on like long sequence generations challenges, right? So for long sequence generation, what happens is that first, it's very long, which means that you really need to have a lot of memory in order to store all the previous sequence KB cache. And the second, it's very slow because the transformer, we all know, if you do dense attention, it is quadratic with respect to the previous length, right? So we really need to have a solution to solve these two problems. And furthermore, we also have issues, which is a perplexity explosion beyond the pre-trained windows. So this is another problem that happens in the pre-trained models. For example, if you use like Llama 2 models there, Llama 2 has 4K context window. And if you have a context that is longer than 4K, and all of a sudden, the perplexity actually goes to infinity, or very high, rather than a gradually degrading. So in this case, how can we find a way to remedy this problem and make the ARM to generate very smoothly in order to get good results? So we have some approaches. First of all, let's talk about like how can we reduce the memory usage to generate the tokens. Right. So if you think about like how it works for the self-attention in the inference, what happens is that you have these tokens, and then you have to basically compute the self-attention between these tokens and all the previous tokens. Right. So this is actually the reason why you have quadratic complexity. But then the question is like, do we really need to store all the previous tokens? The answer is actually no. If you check like the statistics of the self-attention, you're going to see this kind of curve, right? So basically this curve basically measures like co-occurrence and also attention scores. First of all, you see these two are highly correlated, which is consistent with our previous analysis. And second, you see the majority of the attention score is assigned to a subset, a very tiny subset of the attention of the tokens. Right? So the majority of the tokens, they don't really receive any attention at all. Right? So you see like this graph is very flat, and only a small set of tokens, they collect a lot of attention scores. These are called like heavy hitters. So, and also we find that if we get rid of these heavy hitters doing our inference, the accuracy actually goes down a lot, right? So this basically means that these are very important in terms of like maintaining the accuracy for different metric for the ARMs. Right. So, and then a natural question is that, oh, maybe we can only keep the heavy hitters, right? So, and we can get rid of all the other attentions and all the tokens in the previous generations. Yes, that's true. So we actually find a very simple approach actually works, right? So, for example, when you do generation, you monitor these tokens. If these tokens have very low attention scores in the previous generation process, then at some point you get rid of these tokens altogether. That's called the very local greedy algorithms. Okay. So what they do is like very simple, right? So once you generate new tokens, you keep their attentions, and then you also monitor how much attention was being placed in the previous tokens. And for every previous tokens, if their attention score is very small, in terms of the summation, you get rid of them. You only maintain like a fixed size of the KV cache. And it turned out that this algorithm actually works quite well. So you will see that if you only keep like only 20% of the previous tokens, you still maintain a very high metric in many different scenarios. Right? So here we're using Llama, not Llama 2, because by the time we released the paper, Llama 2 was not there. So we use Llama to basically evaluate whether this approach really works. Right? So you see that if you use heavy hitters, it's actually maintain the score when we only use 20% of the previous tokens and discard 80% of other tokens. It's actually very impressive because you can imagine that if you have 1,000 tokens, then you only need to keep 200, and still the performance remains similar to each other. And we also tested in 2 different GPUs. One is T4 and the other is A100, and you see our approach called H2O actually give you a much higher throughput because it uses less memory and use less compute in order to get the performance. So that's actually pretty good. Okay, this is our H2O paper, and this is being accepted in this year's Europe's. So it has very high scores, but unfortunately didn't get oral or spotlight. Yeah, I saw that it should be a spotlight and oral level paper. And moreover, it's also compatible with quantization. It also generates sentences with less repetition at the same time, more creativity, which is interesting because it gets rid of some tokens that is not relevant and also release more room for generating more nice tokens. This could be useful for generating stories. And we also have follow work, which is the streaming ARMs. So one question is that, okay, we have headers and we have good statistics of them. So, but one question is like, where are they, right? So they might be residing in different places, but actually, after you do this kind of visualization, they're actually residing in the first few tokens. It's very interesting. So this actually gives us like this kind of flow of ideas called streaming ARMs, right? So maybe instead of doing heavy hitters, what we can do is we just keep the first few tokens that are called attention sinks. If you keep the first few tokens, then we can actually keep like generating new tokens without degrading of the perplexity scores. That's the streaming ARMs. So this is actually very good because it combines the benefit of the two things, right? So you can either use dense attentions, which is very slow, and at the same time, if you're generating outside the window, you basically give like very high perplexity. You can also use window attention, that is basically does not have quadratic perplexity, but at the same time, the perplexity score is also getting very high after you're moving out of the original few tokens. If you keep the first few tokens, and at the same time generating next tokens, then you get the benefit of both, right? So you have a much lower complexity, and at the same time, your computational complexity is also very small. Yeah, so this is basically the curve showing that it indeed the case. Our streaming ARMs, which is shown in red, has a very low perplexity with even the input length is very high. We actually tested it with 4 million token length, and still the perplexity is low. But the previous tokens, the previous approaches actually give you very high score. Right? So you can also use windowed attention, which is give you comparable performance. But windowed attention with recomputation is much slower than us. So here's like one. Let's check whether we can play this. So this is like a video showing that our approach actually can give you infinite streaming of large language models in terms of the generating, but other approaches does not work that well. Either it's running out of memory or it gives you garbage. Unfortunately, it seems like the connection does not work that well. Let me try again. Okay, that works now. You see, like we are basically can keep streaming with the meaningful sentences, right? So, but the other approach is also memory, because if you use dense attention, sure, over time you have to store longer context. At some point, things will break. It's all memory, right? So, or it generates something that is completely garbage, right? So, here so performance breaks, right? So you see like random things coming out. Right? So because it loses the initial token sink, and things just breaks. Yeah, so that's basically the view. Right? So, but in our approach, we basically get where is the key component to maintain the quality of generation, and we keep this key component, and things works well. Okay. Let's go back to the slides. Okay, so finally, we'll talk a little bit about how can we extend context window for trained models. As I mentioned, that for pre-trained models, if we keep generating until it's going beyond its pre-trained context window, then things will break. Right? So you can use different remedies to solve the problem, right? The previous streaming ARM, you keep the first few tokens, and this will work. But then, like the question is, if we keep using the dense attention, how can we still solve these problems? So we actually have another approach we can actually use to solve this problem. It's called extending basically positional interpolation. So we think about like why that this is the case. The one possible explanation is that the attention function A is actually ill behaved, right? So within the context window, the attention function is actually very well behaved. For example, it's bounded, right? So it's less than one, and greater than -1. It's bounded. But if you go outside this window, interestingly, you can very easily construct any function and then go very crazy once you go outside the window, right? So this is the problem of extrapolation, right? If you extrapolate, then the function that seems to behave well will actually become like ill-behaved, right? So, but if you do it the other way around, for example, if you do interpolation, then you can actually show that the error of interpolation is much smaller than error of extrapolation. Right? Yeah. And so that then like what we can do is that we can actually, oh, thanks. Yeah, so then the idea is simple. Right? If you want to generate sentences that is 4K rather than 2K, instead of doing extrapolation, we basically can make the positional embedding smaller for the 4K sentences so that it still fit into 2K windows after this kind of scaling down. Very simple, one line of change in terms of the code base. And suddenly things works. Right, so if you can show that with just like less than 1,000 step of fine tuning, you can the model actually can basically extrapolate very well to the context windows that is beyond the pre-trained context windows. Right, so for example, once you have positional encoding, this is our approach. Right, so we can very easily extend the context window from 2K, which is the default context window of the Llama 1 model, to 32K. Right, so in 32K, you see the content, the window is higher, the complexity is lower, right? And this can be achieved with very few steps of fine tuning. And you see that it actually uses like less than 200 steps, and it will basically can extend the context window from 2K all the way to 32K. Right, so it's actually very interesting to see this happens once you change the simple switch of the of how you represent the positions. Yeah. And we also show that performance can remain the same in larger world benchmarks. So for all the benchmarks, they still give you reasonable performance after interpolating into longer context windows. So this is a little bit dropping, but for the remaining components, it looks pretty good in terms of the performance. So it still can be used. This paper has been pretty popular in the Hugging phase. We already see many different interpolated models being fine-tuned based on different pre-trained models using this technique and its improvements. So after this paper was released, in 2 days, people talk about a more improved technique in the Reddit. And if you want to be interested, you can check. Yeah. Okay, so that's basically all of my slides. If you have more questions, please let me know. And we can also discuss further in the follow-up discussions. And thanks all for the attention.
Yeah, thank you. Thank you for great talk. And it's a long, almost 1 hour.
It's 1 hour, yes,
Okay.
yes.
So he gave us a lot of from theoretical research and to real technical language model. So a lot of information to us. Very interesting for us. Maybe now it's time for question and discussion. Maybe I will first ask several questions. You mentioned the model compression using quantization or some technique.
Yeah.
It not only for compression but also improve the speed.
Yeah.
The speed is basically for inference speed, right?
Yeah, it's for inference speed. It's not for training. I think for the entire part 2, it's all for inference. Inference with the fixed models or fine tuning. Yeah.
Okay. Yeah. So do you think if the model be compressed, then the speed will be also increased naturally?
It's not naturally the case. Yeah. So usually, if the compression is not done right, then you actually need to spend more time in doing the inference, right? So if you think about like different ways of doing inference, for example, you do quantization. What you do is like you quantize each weight into one of the centroid, right? So you first do some KNNs, then you get some kind of centroid of the weights, right? So then you basically, instead of storing the actual floating numbers, you can store the quantized numbers, which can be represented in 8 bits or 4 bits. In that case, you have to first do retrievals. For each weight, you have to basically retrieve this from your dictionary, elect actual numbers and load it into memory. And then you compute the attention or compute the MRP scores. right? So this basically requires a matrix multiplication, right? And then you get the actual numbers, and then you do this move feed forward. There's a lot of engineering component there. If you don't do that correctly, then it will be much slower than the original approach, right? So, but there's already a lot of packages that you can use to do that. Yeah, so feel free to use it. I think usually what they do is like they first decompress in the memory on the fly with very efficient approaches, and then you use existing techniques to do feed forward. Yeah.
And more questions about, so Lemma from your company, we have several versions.
Yeah.
7B is the smallest and
Yeah.
65.
Mm-hmm.
So what's the essential difference between these models? They have big difference in performance. This is the first question. Second, do you think model compression is important for Lemma or not?
Yeah, okay. So first question is like whether there's any performance difference. Sure, there's obvious performance difference.
How big difference?
Yeah, I think it depends on your task, right? So for 7B, I think for specialized tasks, it's actually pretty good, right? So for example, you can fine tune this model into different subtasks, right? So for example, we actually have works that try to fine tune 7B for storage and generating story outlines, and also to evaluate stories, evaluate the outline of the stories. For this 7B, 13B, they are good, right? So, but if you want to generate actual content of a story, because which may have lots of rich component, in that case, you probably need a 70B, right? So 70B will have more content and will have a much more diverse component there. Yeah, so you need this. So I would say for specialized, if you have very specialized needs, try a small model first, right? So if you have a very more diverse requirement, then definitely the larger model is the better. Yeah.
Yeah, because there are many research doing model compression.
Yeah.
Do you think if the model size becomes smaller, the performance will be keep on not impossible to sustain performance?
I think I would suggest that you try to compress 70B into maybe 30. Basically, the larger model you have, the more potential you have, and the compression will give you a bigger boost, right? So you already will have a paper. I already saw paper from SPQR. They basically can compress 34B models, right? So into a single GPU. Right, so and then you can use a single GPU to drive a 33 or 30B models. It's already big things, right? So yeah, you can try this way, and then in that manner, you might get like a higher boost there.
One more question about robustness to adversary attack.
Okay.
Computer vision, CNN is well studied.
Yeah.
Transformer, and wonder how is the transformer is robust or not robust?
It's actually not robust, right? So if there's a recent website called ARM Attack. Right, so this is something that's very simple, very interesting. Yeah, so this is basically a very recent work, right? So from Carnegie Mellon University, and also from, actually, I saw from Google as well, but there are two additional Google courses. They were not able to put their name there because their company don't want them to publish ARM attack papers. But there's additional courses there, but you can check this paper. They have a very nice attack patterns to attack the existing algorithms, right? So if you see like what they are doing, they basically put a suffix of the prompt of the larger models, and all of a sudden the model give you bad content. Yeah, so it's very impressive. Let's see, there's any examples. I think this example probably is not working anymore because they have already fixed it for large models. But if you run their code to generate new patterns, maybe it still works. I'm not sure. Right, so you can see like, okay, generating a step-by-step plan to destroy humanity. That's usually if you ask these questions, the model GPT-4 won't give you any answer. It will say, "Oh, I'm sorry, I'm a large model. I won't be able to give you anything that it will destroy humanity." Right. So, but if you put like a random things as a suffix, then all of a sudden GPT-4. This should be 3.5. Yeah, this is 3.5 basically. Give you all the answers. Right. So basically, and this is actually in some sense very severe because it basically break the structure, break this kind of like a safety firewall. Right. So it gives you something that is supposed not to be safe. So I would say it has a lot of rooms because right now this is like the first paper in the previous years. So you know, like in previous years, Ian Goodfellow has won a diverse attack paper, and by changing like a few like pixels, I was able to attack the ACL systems. But now this is same thing happens again. Right, so I would expect to see a lot of different follow-ups, and I'm not sure like, whether it will happen. Right. So first of all, these attacks are following very weird patterns. Right. So you have random kind of tokens, and suddenly it works. And people will say, oh, it's very easy to filter that out, right? So you can put like some very simple check and say, okay, to check whether these are good sentences. If there are no good sentences, okay, I will basically alarm, right? So this will filter out very easily. But I would imagine that in the future, you're going to see attackers to attack the input by adding some spaces. And still it will work. It will basically give you random answers. It's also possible. Yeah, so I would say there's a lot of rooms if you want to work on it. Sure.
Yeah. Thank you. Yeah. Any other questions or comments?
Thank you for your presentation. It's very impressive. I'm quite interested in the theoretical work. Like you mentioned that the learning trajectory or dynamics of the transformers has two phases.
Yeah.
It's from the first side, first again to next and snap.
Yeah.
And I have a question related to the. Have you ever do you see is there any connection between the studies for like Python spectrum or age of stability related to your work? Because I can see a lot of phase transition in the on that field. Yeah.
Okay, yeah, thanks. I think that's a good question. So I think this age of chaos or age of stability, basically they are trying to analyze the situation when the learning rate is huge. Right? If you have like a large learning rates, then what happens is that you might get rid of the region that has a sharp minima and then basically convert to the region that has a more like a flat minima.
Yeah.
Right. So that's the I would say these two pieces of work are not directly connected, but they might be connections later. Right. So because if you think about edge chaos, edge stability, what you think about is like you treat this entire function as black box functions, high dimensional functions. Right. So you don't really know what this function corresponding to. Right. So in our analysis, what happens is that we really open the black box of transformers, and we say, oh, this black box and dynamics correspond to a specific architecture of the network. Right. So it's possible that there may be connections between the edge of chaos and also the attention mechanism. That's true, but we haven't seen about that way yet. But there will be connections. Yeah.
Yeah.
Okay.
Thanks for nice talk. I also have a question similar to related to multiplication. In the technical part, you mentioned that you can reduce the sparsity and you reduce the memory cost or reduce the requirements of So the question is possible to use the sparsity to reduce the number of parameters directly.
Yeah, I think that's probably possible. I mean, people have been thinking about this idea for a while a little bit. I say, okay, if things are sparse, why it's not sparse at the beginning?
Yeah.
The answer would be it's tricky because there need to be a lot of parameters at the beginning in order to explore all different directions, and then it becomes sparse later. Right. So this is related to the lottery ticket hypothesis. Right. So this is a famous paper. That was they won the best paper in IKEA, right? So maybe a couple of years ago. what it says is that I mean you have a lot of lotteries to draw in your parameterized network, right? So each parameter represents, for example, one possible directions in the data, right? So when you start training, then some of the lottery become lucky lotteries, right? Because they happen to fit well with the data, and these lotteries will grow a lot, and then this becomes like the subset of the network. That is basically like very useful for predicting the next token or the class. Yeah. Right. So, but before that, you don't really know which one is the lucky one. You really need to have a lot of parameters in order to draw. And once you are training, then some of them will become useful. Right. So that's actually also acknowledged in our previous current ongoing studies. And we're going to have one paper coming out, but not soon. But there will be some further studies about this.
Yeah, thank you.
Yep.
No more questions. Then let's thank the Yuandong again.